Hi everyone, thanks for checking out this video. So this video is going to be about how to implement the Gillespie algorithm in Matlab. So if you're watching this, I'm assuming you've already seen my other video, the introduction to the Gillespie algorithm. So that explains sort of like the concept and sort of like step-by-step how to do the Gillespie simulation. But if you haven't seen that yet, I'll include a link in the description to it if you want to check that one out first. But anyway, the reason I'm making this video is because I already made a video showing how to implement it in Python. And usually I do my work in Python because that's my favorite language. But it occurred to me that a lot of people also have to use MATLAB for like school, and especially if you're working like in an academic setting, you may be using MATLAB. So even though I'm not personally like a huge fan of MATLAB, I thought I'd make a Gillespie tutorial for MATLAB users too, in case no one's using MATLAB. Okay, so before we get to the coding, I'm just going to quickly review the system we're going to be simulating. So this is the ODE, but remember, this isn't going to be an ODE simulation. This is just like the ODE equivalent of what we're going to be doing. So we have a gene X, and we're going to be modeling the transcription and degradation of this gene. So we're going to say that our gene X is being transcribed with rate K, and then it's being broken down with degradation rate gamma, and then our entire degradation term is gamma times the current level of X, because remember it's like some fraction of the current level that's being broken down. So this is our simple ODE here for the transcription and degradation of some gene X. And then if you remember for the Gillespie algorithm, just to give a quick review, what we're going to be doing is choosing the time point of the next event, and then choosing which event that will be. So with this system, there's two possible events. There's the event where a new RNA is transcribed, which means that the level of X will go up by 1, and this creation of a new mRNA is happening with rate K. And then the other event is that an mRNA can be broken down. And when this happens, the level of X will be going down by 1. And this event will be happening with rate gamma X. Okay, so that's a quick review. But again, I encourage you guys to watch my other video going through the Gillespie algorithm in more depth. So I'll link to that in the description too. But yeah, so for now, let's get to the coding. Okay, so the first thing I always do with MATLAB is I start off with these 3 lines here. So this just like clears our workspace. We want to like clear out any variables that might be defined already, and then clear the command window. And then so the next thing we're going to do is it's going to be I don't know if you guys have watched the Python video already, but it's going to be pretty similar to that, except just with the MATLAB syntax. So we're going to first define our endpoint when we want the simulation to end. So we'll call that tEnd, and we'll make it 100 for now. So basically, we're going to run the simulation until we reach 100 of whatever time unit we're working with. And then next, we need to define our parameters. So we have 2 parameters here. So there's K and gamma. So remember, transcription rate and degradation rate. So I encourage you guys to like play around with different values of these to kind of experiment and test things out. But for now, I'm going to make K 2, and gamma will be 0.1. So if you guys remember, this should give us a steady state of 20. So remember, to find the steady state, we just set the ODE equal to 0, and then solve for whatever we want to solve for. So if we set this to 0 and then do the algebra, we get the steady state of X is going to be K over gamma. So it should be steady state of about 20 in this case. So next we need to define some things just for running of the simulation. So we're going to define t. This will be the first time point. This will be 0. This just means we're going to be starting at time 0. Okay, so before we begin the actual simulation, I'm going to quickly explain to you guys how dynamic arrays work in MATLAB and how it's different from Python. So if you guys remember in Python, the way we like set up dynamic arrays is we kind of define it as being some empty array like this. And then once we have our empty array, we can append values to it using the append command, and this will sort of keep adding new values to the array. In Matlab, it's a little bit different. So the way it works in Matlab is even when we haven't defined the array yet, we can just go ahead and start define it by setting the first value to it. So like with this command here, this will be setting the first index of this test array, which we haven't defined yet, but will be defined with this command. We can set this to be 100, and then we can sort of keep adding to it by just setting whatever index we want to be whatever value we want. So as you can see, when I ran this command here, it updated test to be to now have 2 elements. And we can keep going, so maybe set the third element to 300, and it'll just keep adding like that. So that's sort of how dynamic arrays work in Matlab. You don't need to predefine them in advance. You can just go ahead and start adding the values, and when you add the first value, it'll be defined. Oh, and by the way, if you guys didn't know this already, so this is one of the things I don't really like about Matlab is that in Matlab, the indexing doesn't start at 0, like most other programming languages. It actually starts at 1, which if you're sort of new to programming, you may think this makes more sense to start the indexing at 1 instead of 0. But I kind of just don't like this because if you're used to programming in other languages, you're used to the indexing starting at 0, and that's just kind of the convention for practically every other language besides Matlab. But yeah, so in Matlab, it starts at 1. There's no index 0. So that's something to keep in mind. Okay. So let's get back to it. So anyways, so we're gonna have our values of x stored in this x array. And even though we haven't defined the x array yet, like we said, we can just go ahead and define the first element of it like this. So the initial condition for x is going to be 0. So we'll define that here. And then I is going to be like a counter variable in the while loop. It'll be incremented each time the while loop goes through an iteration. So we're going to define this at 1 to start with. And you guys are going to see in a second where we're using I. Okay, so the way the actual simulation is going to work is we're going to have a while loop. It's going to be executing while the most recent time point is less than whatever we set our t end to be. And oh wait, I actually made a mistake here. Sorry. So this should actually be t should actually be an array here that we're setting up. So this should be t, the first element, is being set to 0, not just t as a variable by itself being set to 0. So sorry about that. So, but anyway, so yeah, so the while loop is going to be executing while our most recent time point is less than t end. Okay, so if you guys have watched the Python video, this is going to be this part is going to be pretty similar to the Python video in terms of the actual kind of the mechanism of how we're actually doing the simulation. The only thing that's going to really be different is the syntax, but so just go through and try to explain where the syntax is different. So the first thing we're going to do is put all of our rates in an array. So we're going to define this zeros array, dimensions 1 by 2. And then we're going to set first element to k. And then second element will be gamma times the current level of x. So remember, we're using I here to get the current level of our x array. And so these rates here, remember, these are just these rates here. So the reason we're putting them in an array is just so they're easier to manage, and so that we can keep track of them, and then also we're going to want to get the sum of them too. So we put our rates in that that array there. And then we're going to get the sum just with the sum function. Because remember, assuming you guys have already watched my intro to the Gillespie algorithm video, the way we calculate the next time point is going to be by taking a draw from an exponential distribution, using the rate sum as the parameter for that distribution. So okay, so another pet peeve, annoying thing about Matlab is that in order to use the actual exponential distribution function, you need to buy an extra toolbox thing. So if you guys remember with Python, we just had this this numpy command to draw from an exponential distribution. But for Matlab, to be able to do that, they want you to buy some extra an extra package, which I didn't want to buy, so I'm just not going to do that. But luckily, there's still a clever way we can get an exponential random number. So the way to do that is by just taking a regular random draw, meaning uniformly distributed between 0 and 1. We just take a random number between 0 and 1, and then we can actually transform that into an exponential random number. So the way we're going to do this is, set R1 to random with argument 1. So this will give us some random number between 0 and 1. And then this will be the transformation here. So remember our increment of time we call tau. And then this is the transformation here. You guys, I guess, might need to kind of just take my word for this for the moment. Although if I have time in a future video, I may explain how we derive this. But yeah, for now, maybe you guys can just take my word for it. So this is the transformation. So we have our random number between 0 and 1. So we're going to take the log of 1 over that random number and multiply that by 1 over the sum of the rates. So this is going to give us some exponentially distributed random number tau, which will be from an exponential distribution where the mean of that distribution is 1 over the sum of all the rates. And then, so the way we get, now that we have tau, the way we get the next randomly chosen time point is we're gonna make the next element in t. We're gonna set this equal to the last element in t plus tau, right? Yeah. So our next time point is going to be the current time point plus this random number tau that we just picked. Okay, so now that we've chosen the next time point where the next event will happen, we need to randomly pick which event that will be. So if you guys remember from the intro video, the way we do this is by just taking a random selection of these events where we weight the probabilities of each accordingly. So the probability weights of each will be the probability of this event happening, x going up by 1, will be k over the sum of all the rates, and the probability of x going down by 1 will be gamma times x over the sum of all the rates. So that's how we weight the probabilities accordingly, and then once we do that, we just take a random choice between them. So the way we do this in the code is we're going to pick another random number called R2 using the same rand command here. So we pick a random number R2, and then we're going to, sorry, I'm just going to type this out and then I'll explain it to you guys. So okay, so what this is checking here is we're gonna multiply our random number between 0 and 1 by the sum of the rates, and then we're going to check and see if this is less than, sorry, this should actually be less than or equal to. So we're going to check if our random number times the rate sum is less than or equal to the current value of the first rate. And then if this is true, then we're going to choose the event where x is going up by 1. We'll be choosing the first event here. And then if that happens, we want to set the next index of x to be whatever the current value is plus 1, because it's going up by 1. And so if that's not true, we're going to say else if, really in this case, since we only have two events, we really could just say else, because we know that if it's not the first event, it must be the second event. But I think I'm going to write it this way just because it's good to get in this habit and sort of show you guys how it's done if you have like more than 2 reactions and you need to test a bunch of them. So even though we could just say else, because we already know if it's not the first event, it's going to be the second event, I'm going to still write it out anyway, just so you guys can see, so you know how to do it in cases where you have more than 2 possible events. So I'm going to type this out really quick and then I'll explain it. So. Okay, so I know this is kind of like this line looks a bit confusing, but all this is saying is that, okay, so if we know this random number times the rate sum, if this isn't less than the first rate, we're going to check and see if it's greater than the first rate and less than or equal to than the sum of the first and second rates. So we already know, because there's only 2 events this time, we already know that if this first if statement is false, we already know this will definitely be true. But I'm still writing it out anyway so that you guys can see in case you have other simulations you're doing where there's more than 2 events. So if you had more than 2 events, you would just sort of keep repeating this line to check and see where this number R2 times the rate sum falls. So basically, we're checking to see if it's, first we check if it's less than just the first rate, and then if not, then we check if it's less than or equal to the first rate, and then if not, then we check if it's greater than the first rate and also less than or equal to the sum of the 2 rates. And then let's say if we had a third event, then if those first 2 checks came up false, then the third check would be to see if it's greater than the sum of the first 2 rates and less than or equal to the sum of the 3 rates. So we're kind of choosing which event's going to happen by checking to see where this random number falls in this incremental summing of these rates, where this random number falls. But yeah, so if this is true, which we know that if we reach this line, it will be true because we only have 2 rates this time. But if this is true, then the next value of x will be the current value minus 1. Because remember, we're updating with this event here. Okay, so then the last thing we need to do, and this is of course important to remember, I've screwed myself up and run into a lot of bugs sometimes, just like forgetting this line. But we have to always remember to increment our counter variable I here. So we're going to say I equals I plus 1. So very important but often forgotten line here. Okay, so this is all we need for the simulation. So this is going to run and keep executing as long as our last value of t is less than t end. And then once it reaches t end, then it'll stop and exit the while loop. And then so the last thing we can do is plot the results. So we can plot our time points and then the values of x. Okay, so let's give this a try, and hopefully it'll run okay if I didn't make any mistakes. So let's see. Okay, yeah, looks like it worked okay. So as you guys can see, of course it's a stochastic simulation, so it's not, even the steady state isn't really like that steady, but you can kind of see that as we expected, it's getting up to around 20 and then kind of fluctuating around 20, which is the steady state. And you guys can see we can run it a couple times, get some different results every time. Yeah, I'll just show you guys a couple just so you can see what it looks like. Yeah, so looks like it worked okay. So that's all for this lesson. Like usual, I'll put the code up on my GitHub if you guys want to download it from there. So I think when I do MATLAB lessons, I'm just going to call the file the same thing, except instead of .py, it'll be .m. So the Python file that we did for this was transcription ssa.py. And this one will be called transcription ssa.m. So this will be up on GitHub. If anyone has any questions, let me know. I'll try to answer them if I can. And yeah, so thanks for watching, and see you next time.